NASA's Perseverance rover just delivered one of its most intriguing science results yet from Jezero crater. A new Nature paper reports tight linkages between redox active minerals and organic molecules in rocks from a unit called Bright Angel. And that combo is exactly the kind of chemical pattern scientists look for when they're hunting ancient habitability, and even possible biosignatures. Let's unpack what was found, why it matters, and what comes next. Scientists analyzed outcrops in Jezero's Bright Angel Formation and found associations between iron and sulfur-bearing minerals and organic compounds, arranged in patterns consistent with redox processes. That's the give and take of electrons that powers chemistry, and, on Earth, a lot of life. The study argues these rocks preserve a redox stratified environment, think chemical layers, that could have supported microbial metabolisms long ago. Important caveat: the paper does not claim life has been found. It reports geochemical conditions and textures that are compatible with habitability, and preserves organic mineral pairings that, on Earth, often concentrate and protect biological material. Welcome to DTU Research Database. Jezero is an ancient lake basin fed by rivers. Deltas trap and layer sediments, prime places to preserve organics. Bright Angel sits along a former inflow channel called Neretva Vallis, and the texture suggests sedimentary deposition followed by chemical alteration as waters and oxidants move through. To decode the chemistry, Perseverance used PXL, an X-ray fluorescence spectrometer, to map elements at hair-thin scales, Sherlock, deep UV Raman fluorescence, to sniff out organic functional groups in context, SuperCam laser spectroscopy for mineral chemistry, MastCam Z stereo imaging for textures and layer geometry. Put together, these tools don't just say there are molecules here. They show where they sit inside the rock fabric and what minerals are touching them. That spatial relationship is the big deal. Redox-driven associations means the distribution of minerals and organics appears guided by electron transfer chemistry. For example, iron toggling between Fe2 and Fe3 can create chemical gradients. Sulfur moving among sulfide-sulfate forms can indicate oxidation fronts. Organics often adsorb to iron oxides or precipitate with sulfides, which can shield them from degradation. On Earth, such patterns frequently emerge in deltaic and lake sediments, where microbes harvest energy by shuttling electrons to iron or sulfur. The paper carefully notes abiotic pathways exist too, but the co-location and fabric they report are exactly the kind of clues astrobiologists chase. Not yet. A biosignature requires ruling out non-biological processes with high confidence. On Mars, radiation, perchlorates, and oxidants can modify or create organics. Mineral surfaces can concentrate organic molecules without life. The study's authors frame the results as evidence for a once habitable, redox stratified setting with organic mineral pairing that could be biological. But sample return to Earth labs is the decisive step. bright angel rocks show fine laminations and grain-scale textures consistent with sedimentary deposition. The instruments report iron oxides, iron carbonates, and sulfur phases intertwined with Sherlock-detected organic signals. Critically, these features appear organized, not random, suggesting chemical gradients operated over time, likely with intermittent water moving through. On Earth, iron and sulfur cycles are central to many microbial metabolisms. Minerals like goethite, hematite, or pyrite can trap and protect organics, preserving molecular fragments for billions of years. Seeing similar pairings on Mars tells us two things. The chemistry for life as we know it existed locally. The preservation potential for delicate organic compounds in Jezero is real. Perseverance has been caching rock cores that could one day ride a Mars sample return campaign to Earth for ultra-high precision analyses. Compound-specific isotopes, molecular chirality, nanoscale textures, the kinds of tests that can separate biology from geochemistry. Big picture. This nature study doesn't drop the L word, but it sharpens the map to where life's chemical fingerprints would be best preserved, and raises the odds that the samples already cached are the right ones. If you want us to break down the instruments or the sample cores one by one, hit like, drop your questions, and subscribe. The road to answering "Are we alone?" just got a little more interesting.